So that's it. My watch is fast. All right, so time for a check-in. I have a couple announcements. Over here it says lecture and labs. Next week, lecture and labs. Meet discussions do not. That means that I have not found subs for your discussions, but I have found subs or sub, if you will. Professor Alex Ischuk will be doing the lab next Monday, and he will be doing both of your lecture portions. Of course, the lecture portion next Wednesday, 1 week from today, will be exam number 2. And there will, stay tuned for updates about the following week. I'm still working on that. Details provided. There will be a take-home portion of exam number 2. I will email it to you after you take the exam on next Wednesday, and it will be due the following Wednesday. For those of you who have not had take-home portions of exams from me before, you should know that each of your questions is individual to you. That means that you may not photocopy or in any way take another person's problem. Should you lose yours, since it will be in your email, that is hard to imagine, but if you do lose your take-home portion of the exam, you should write to me for another one, and I will send you one that is still unique from everybody else. Having said that, it's open book, open note. You may talk to whoever you want to except me. I will not check them ahead of time. I will not say one word about them, though you may speak to anybody else, including people in this class.
Yes, we
You can ask Professor Ischuk.
Yes.
I will probably tell him not to answer any questions. Travis?
So with the take-home portion and the exam being split into 2 different days, there are 3 different parts to this exam?
Good question. No, there are only 2 parts. There's the part that you'll take next Wednesday and the part that you'll have for a take-home.
Okay.
I expect the take-home portion will be about 20 points, include 1 to 2 graphs that you do have to make in Excel, but I haven't even made it up. I've almost got the final version, which I showed on the display earlier, of your in-class portion of your exam, but I don't even have that yet. Elliot?
When's the take-home part due? I kind of missed that.
The take-home part, so you will get it next Wednesday.
Yeah,
it will be
in the
due
email.
the following Wednesday at 12:30. Or any time before that. How long could it possibly take?
So we email it back to you?
Who knows? No, you print a hard copy and then you bring it to me.
Okay.
You're on when I get doctorate.
So, and it will say, so it will be explicit. It will tell you to drive to a location in Rancho Cordova.
I'm not going.
Secret code, titrate the solution that comes out.
Scavenger hunt.
That is awesome. No, and so it'll probably be a question that takes about a page for me to tell you, and then takes 2 to 3 pages for you to answer, and it'll be worth about 20 points. Yeah, out of 150, still 130 in class. Then I feel pretty confident that you will have time to feel good about the in-class portion. You may not feel perfect, but I hope you will feel good. That is how I'm trying to design it. And that's why it's not done, because I want to give it more time to fine-tune. Marissa?
Are the take-home and the in-class portions like equally weighted, or like last week like 15 was the take-home?
I'm going as high as 20, I think, on the take-home portion. That means the in-class portion will be 130. Yeah, so the in-class portion is by far the biggest part. That's because by next Wednesday, you should know the material. I will say one last thing. The practice exam is relatively closely aligned with the material that you are going to see on your exam. More closely aligned than previous times. However, the practice for exam 2, the yellow sheet that I passed out last time, is more closely aligned and pretty closely aligned. Now, what does that mean? That means if I ask you a question, can I borrow that? Yes. It's a nice thing about color coding things is I can recognize them from a distance even though I can't see them. For example, question number 1, short answer. What are the blah, 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 blah of a solution of HONH2? Well, I could ask a very similar question with a different substance. Think about what the possibilities are. That is a weak base. The obvious choice is I could ask a question with a weak acid, but I could also ask a question with a salt. I could ask a question with a strong acid, a strong base, a weak acid, a weak base. Think about the options. Marissa? When will I be posting the answer key for homework 5? It is already posted. But homework 4 is not, and what I would have said, and will say now again, about homework 4 and 5, is that when I made the key, it was a draft key before I finalized the format of all your problems. So all the answers are there, but you may have to look at different pages. Anyway, they're all there, and it tells you, like, and if you can't find anything, just email me. It might mean it's not there, but I can't imagine because I wrote gory details about all the answers because I realized I will not be here to answer questions, although I will be available by email. Okay. Practice exam answers, great question. I have them. Thank you, Ethan. We teamed up he did the work and I checked it. If there are any mistakes, it is my mistake because I checked it. He has given it to me. I've scanned it. And if you do not see it by tomorrow morning, let me know because it means that I forgot to post it later today. Sorry, what? When am I not going to be here? So I leave on a jet plane tomorrow morning.
Dang, classy.
What's that?
Is it a private place?
Is it a private place? Esperanza? Yes, it is. No, I am. When will I be back again? Oh, yes. No?
They didn't get it.
Thank you. Took me a minute. Any other questions? So, I appreciate all the hard work I'm seeing. I hope and I feel it will be reflected on your scores on the exam. In general, I think it was on the first exam, but not in totality. So, anyway. All right, well, then if that's it, then, yes, Travis.
Will there be a daunting last question during our in-class lecture, or is that in place of that?
You know, you'll have to tell me.
Oh.
It is a surprise. I have rough drafted it, but it is not complete yet. Honestly, in my humble opinion, I would say it's not quite as convoluted as previous attempts, but like I said, your mileage will vary. And it's subject to change because it's not done yet. So Travis? We'll see. Well, then where were we? We were finishing up chapter 18. This will be the last material that's on the exam. I wanted to touch base. I know a lot of people are interested in biological sciences. Actually, just as a quick poll, how many are chemistry majors in here? One. That's right. So yeah, lots of people related to biology, nutrition, pre-med. I mean, if anything, you're more interested in the biology than the chemistry. But you use the chemistry. You know that you have to know the chemistry to study the biology, at least on some level.
It's Sam.
This happened last time. Let's see if we can fix it.
Just stop allowing him to send the file.
Let's see if that fixes it. Anyway, so this is a picture of glycolysis. I'm not going to pretend to understand this personally, but what I can do is I can break things down into tiny, tiny chunks and then think about the chemistry. And for example, here's, I think it says there's 10 steps. We're going to focus on step number 1. It looks like, am I skipping a page?
The others are.
Let's double check. There we go. Somehow I got it. Okay. That's better. So we're going to focus on step number 1. Step number 1 takes glucose. It has a enzyme here and turns it into glucose 6-phosphate. That reaction is coupled with a reaction that turns ATP into ADP. What is ATP? Thank you. Adenosine triphosphate, and I guess it's adenosine diphosphate is the other one. Good, see, biology. Thank you. I'm going to have to get my notes for this part, that's for sure. Glucose, I know what that is. We're going to assume that our glucose is dissolved in blood, for example. Where does this even happen anyway? Probably not in blood, probably in cells.
Yeah.
Yes, thank you. So, but it's still dissolved, it's in there somewhere. And, and what you do, so if you'll notice, you're joining this little red portion down here, which is HPO4 2 minus. And I'll put the formula up here. So this is glucose. I'm going to put the formula for glucose 6-phosphate. That's an O. CO3. Plus an H2O, water molecule. Why are we talking about this now? That's a rhetorical question. We're talking about it because of free energy and the idea that this has a delta G naught of 13.8 kilojoules per mole. That is a positive number. Is this reaction with that positive value for delta G spontaneous or not? It is not spontaneous, exactly. What we're going to do is we're going to then couple it. That's what this little double or intersecting arrow means right there. With ATP going to ADP. I'm just going to write ATP with a 4 minus charge in the aqueous phase. Plus H2O liquid goes to ADP minus 3. 3 minus. Plus HPO4 2 minus hydrogen phosphate. Plus hydrogen ion. This reaction has a standard free energy of reaction of minus 30.5 kilojoules per mole. Those of you taking Bio 402 or Bio 400 if you're an ARC, do these values, are these things that you've talked about in class? Not yet? Maybe in kilocalories per mole, that's another set of units. Yeah. So do you know the relationship between kilojoules and kilocalories per mole? It's the same as joules to calories, 4.184. So if you see kilocalories, these numbers should just be divided by about 4, really 4.184. Whatever units you use though, this top reaction, non-spontaneous, this bottom reaction is spontaneous. They occur together. And when they do, you get an overall reaction. Then we add them up. We cross out things that are on both sides. I see a hydrogen phosphate on one, hydrogen phosphate on the other. Looks like I got a water and a water as well. And then I write what's left. And in a very similar way to Hess's law, when we did Hess's law and you add reactions, you add their delta H values. You can also do that with delta G values. Add reactions, add delta Gs. And if you do, you get a negative 16.7, meaning that the two reactions, when coupled together with their negative value of delta G, that is a spontaneous process. And depending upon who's doing it, I've seen different versions of these two reactions. For example, if you see H plus and HPO42 minus, I mean, this could be hydronium. There are other ways to write this, but this is the general idea. Any questions about this? Honestly, I should probably be asking you questions, Bio 402 students, about this, but... So now let's talk about what makes reactions coupled. We've seen a couple cases where reactions are coupled, and in this particular case, one, the reactions have to occur in the same place. That seems pretty obvious. And then two, what you typically see is that reactants and products in one of them are also, so things cancel out. Like either one reactant or product or more than one cancels out. So at least one reactant or product, or I guess I'll just say it generally, at least one species cancels out. Of the, what I'm calling here, the overall reaction. And note, the note here, well, I haven't explicitly said it before, but Hess's law works for delta G values as well, and I just want to be clear about that. Hess's law works for delta G values, it works for delta H values, and I guess, just to be clear, if it's delta G or delta H, when you add reactions, you add the delta G or delta H values. I would say that Hess's law works for equilibrium constants as well, with the caveat that when you add reactions, you multiply equilibrium constants. So, and these are some of Hess's law. These are a few of my favorite things, as adding reactions, because what you can do is you can show if a reaction, if the overall reaction is going to completion or not. And so I will point out to you that on your homework, you have, on your last couple of homeworks, I specifically put find Kc for a reaction that was a Kb or a Ka flipped. That is useful information. I want to do one other example of coupled reactions. And the other example, broadly speaking, is what I would call the KSP times KF. And I know it's not in the thermodynamics chapter, but I've gotten a lot of questions on it, so I wanted to go over it. And to do that, do you have your, can I see that practice exam again? Because I noticed there was one on this practice exam as well. Page 7 of the practice exam, number 8C. It says, what is the solubility of cadmium carbonate in 0.00500 molar sodium cyanide? And I won't write out the rest, but the hint is that there's a KF value for the complex ion involving cadmium and cyanide ions. And so for this process, I'm going to write out the KSP reaction for cadmium carbonate. And no matter how many times I write cadmium, or try to write cadmium, I always want to write calcium. That's why these D's look weird. This is a KSP reaction. KSP reactions are dissolving reactions, solid going to aqueous ions. KSP for this, listed on the front sheet, 4.96 times 10 to the minus 9. Then the KF value for the cadmium cyanide complex, 3 times 10 to the 18. When you write a KF value, whatever, KFs mean, F means formation of this complex ion. So that means it is a product. And similar actually to what we've called delta HF and delta GF, which were formation for thermodynamic things. There's 1 mole of whatever the product is. My KF value is very large, so I'm just going to put the single arrow there to indicate that this reaction goes to completion. But take your cadmium ion and your cyanide ions, and have them be reactants. Have them take whatever number of ions you need to make the reaction, to balance the KF reaction. KF for that, 3 times 10 to the plus 18. When you add them, you will cancel the cadmium and be left with everything that's not canceled. Write everything that doesn't cancel out, and then when you multiply, or so when you add reactions, you multiply their equilibrium constants. And you should get a value, well, 10 to the minus 9 times 10 to the plus 18, somewhere around 10 to the plus 9. with a value of 10 to the plus 9, will this be a reaction, this overall reaction, this one down here, does it go to completion or not? Yes, it does. Because we have seen two different options when you get to the bottom of this. One, the reaction goes to completion. Find your limiting reactant. Done. The other one is the KC is less than 1/10,000, and you have to have a nice table with X's. And the reason I really wanted to go over this, two things. One, it's a great example of coupled reactions. It's actually, this is what I love about chemistry over biology. I respect biology, right? I'm struggling. But look, here's my cadmium. And then it cancels out. Very clear coupling of the reactions. Over there, I'd say the waters are a little muddier. They're still coupled, but still happens. So. And then finally, why is this such a good example? Well, I would like to talk about the fact that I have said at least 10 times in lecture, always deal with your largest equilibrium constant, your largest K first. And that is true. Except here. And what I want to go over is why it's not true here. Look, 10 to the plus 18, I think that's the biggest one. Can we agree on that? I think we can. However, it involves a reactant that is a cadmium ion. And we don't have any cadmium ions unless some of this is dissolved. So this is a special case where we have to deal with the KSP reaction first to create cadmium ions before we can take them away. Anyway, that's why, like, okay, you always deal with the largest K value first. In order to deal with the largest K value, you say, well, I need cadmium ions. I don't have any until this happens, so that's why we have to do this coupling. I don't know if you have any questions about that. Okay. How do you do stoichiometry for this? Well, you could, well, what I would suggest, does the problem even tell you how many liters there are? No. So you can't do moles, and you don't need to. You're going to actually set your amount of cyanide as your limiting reactant. This is solid, so it doesn't matter. And then, and you'll see this on the key. Ethan and I were working on it. In an ice table, this is going to have minus 4x to get rid of all this stuff. And you just have to remember that your solubility is always just x. So it'll be 1/4 of the 0.005. And that'll be the answer for that. Anyway, good question. Now, I've told a couple of people this. I might as well tell the whole class. If you see a question like this, it will be exactly like this. So, who knows? We'll keep an open mind. We'll be prepared for it just in case. Okay, so those are coupled reactions. I think that's all I wanted to say about those. That's probably more than I have in my notes anyway. Good. One more thing to cover. It does deal with one of the questions for homework number 5. There we go. We talked about the temperature dependence of the equilibrium constant before. Now we're going to relate it to thermodynamics. In particular, We have an equation that has temperature, the equilibrium constant, and delta G in it. We have another equation for delta G. It goes like this. Delta G naught reaction, the change in the free energy of reaction under standard conditions, equals delta H naught reaction minus T delta S naught reaction. And that's what I'm going to write out now. I don't know about you, but one of my favorite things to do when I see two things that equal the same other thing, I'm going to set them equal to each other. I'm going to put the RT-LNK, or the minus RT-LNK on the left. And for those of you who have been around since Chem 400, you know my next favorite thing to do is to make any equation I have, to linearize it so it looks like y equals mx plus b. That's what I'm about to do here. In order to do that, I'm going to divide through both sides by RT, or minus RT. Theo, can you see my blue work here? Or? Cool. Anybody having problems? All right. That just leaves LNK on the left-hand side. I'm going to break this up into two terms. It's going to be minus delta H naught reaction over R. Times 1 over temperature plus it's going to be plus because I have a minus and a minus here. The temperatures cancel out, and I'm just going to have an R in the denominator. Nothing up my sleeve. Believe it or not, we're done. A line has the form y equals mx plus b. And I'll say more about this, but I'm going to circle everything first. I'm going to end up plotting the natural logarithm of the equilibrium constant on my y-axis. I'm going to plot 1 over temperature on my x-axis, and if I do that, the slope will be related to delta H, and the intercept will be related to delta S. And oh, I guess I have plenty of space down here. So slope slope will be minus delta H naught reaction over R. And the intercept will be related to the entropy, the standard entropy of formation. Example. Plotting to determine delta H and delta S. For the reaction given here, the following data has been obtained. What you're going to do in order to get ready for this plot is instead of doing temperature in degrees Celsius, you're going to do temperature in Kelvin. And 1 over temperature in Kelvin. That's what you're doing here. Let me clean that up a little bit. 1 over temperature in units of 1 over Kelvin. You'll take the natural logarithm of the equilibrium constant. In Microsoft Excel. You'll plot it. You will get what looks like approximately a straight line. Is this seeming at all familiar? Do you remember back to kinetics? Not on this exam, by the way. You remember back to kinetics when we did natural logarithm of little k, the rate constant, and plotted it versus 1 over temperature in Kelvin? What was the slope related to on that plot? The activation energy, thank you. Now, the slope, and you'll have numbers when you make this in Excel, when you add a trend line to it where you display your R squared. We always do that in every single plot. The slope will be related to delta H, and this time the y-intercept will be related to delta S. And so I will ask you to take your m value, your slope, and your b value, and determine delta H and delta S. Questions? Answers then. So your homework 5 is not complete and does not get the 5 points unless it has this plot and this problem correct and turned in. So might only be worth 1 out of the 5 points, but it will certainly be worth that one. Remember, homework number 5, answer key already posted with the plot, I think. But I need that plot turned in. You need to make that plot. That is worth a point to me. Not a whole lot, but worth something. Question?
The temperature in Celsius with the K, are those, in fact, that looks like, I can't, because that's not Kelvin of those numbers.
Sorry. This is K. We might even call it KC,
All right,
the equilibrium constant. Yeah, no, thank you. There's too many capital K's around. K mark closed, and we still have too many capital
So those are each point, like one big column?
So you'll have 1.2, and this was accidental, by the way, but there are 6 points here. You'll have 6 points here. 1, 2, 3, 4. You'll have 6 points on your graph.
Okay.
This graph, by the way, is a little different than the activation energy one. If you remember, activation energy had to always be positive. So the slope of this was always negative. What about delta H? Does delta H always have to be positive? No. So we have no preconceived notions about what the slope of this will be. Could be positive as well. And that just means it's related to endothermic versus exothermic. All right. With that, I think there's one. Oh, we did that one. A summary of a few plots we have made. Well, I sort of already covered this. There's really only 2. Well, how many plots have we made? This is a great thing to think about, by the way, as I make your take home. If I think about plots we have made, here's one. And this, and this is the plot I just did on the last page, and this can tell us delta S null reaction, delta H null reaction, thermodynamic values of interest. And then the plot I just mentioned, natural logarithm of the rate constant. Here's the little k. versus 1 over temperature. Can tell us the activation energy. I mean, in theory, and we mentioned this, although we didn't do it, the y-intercept for that one was related to the A, the pre-exponential factor, which was related to the number of collisions that were in the, well, anyway, it was related to something, but not something that we spent a lot of time. Do we make any other plots? Yes, we made titration plots, that's for sure. Those were pH versus milliliter of base added. We said they can have a lot of shapes. If there was a strong acid, strong base, and went something like this, it was very steep. That was your indicator, and the pH started very low. So I'm just going to label this line strong acid, strong base. And one of the many things we learned about pH calculations, well, there's a buffer region down here. If it's a weak acid, weak base. I think I should have labeled the black line down here. What do you think? I apologize for that. The blue line was a weak acid, strong base. We said that titrations always involve strong something. And then further what we said is that as the Ka value of our weak acid got from negative 10 to the minus 4 to 10 to the minus 6 to 10 to the minus 8 to 10 to the minus 10, this buffer region increased in pH. I do want to point out that it's no accident that these lines overlap up here, because once you're past the equivalence point in either of these, you have excess strong base, and the pH is essentially, it is actually the same. Doesn't matter what you start with. I think we made a couple other plots. Yeah.
On this, you just have two curves kind of on top of each other, superimposed. Is that
Up here?
What you did? Like,
Yes.
like the blue and then the black. Is that like two different titrations? Or?
Yeah, these are two different. So this is strong acid, strong base is the black line. Weak acid, strong base is the blue line. And the point I'm making here, the fact that it only looks like one line, is because the values are the same beyond the equivalence point. I guess I could make this point while I'm up here. So the equivalence point for strong acid, strong base is 7, regardless of the strong acid, strong base. The equivalence point for weak acid, weak base is higher than 7. And of course, all pH values that you write on your exam will have 2 decimal places. Any other questions? I was thinking about it, and I think the one other plot I had you do for the homework was a plot of percent ionization versus initial concentration, showing that as you get to very low concentrations, the percent ionization goes up all the way to 100%. Fascinating. Not going to ask you about it in the exam. Anyway, I think that's all I wanted to say. There's one more slide. That's going to be a companion problem. I'll get that companion problem up over the next couple of days. And we are finished with chapter 18. We are finished with the material on your exam. And we will keep going with chapter 19. It'll take me a minute to pull up chapter 19. Okay. So let's start chapter 19. So chapter 19, just by way of introduction, is about electrochemistry. We've talked about equilibrium constants, and we said that when you study equilibrium using equilibrium constants, it's because you can measure the concentrations of the things involved. Then we talked about thermodynamics, and when we talked about thermodynamics, we're still talking about equilibrium. You talk about equilibrium using thermodynamics when you can measure the energy involved. And now we're going to talk about equilibrium with electrochemistry. You measure, you use electrochemistry to talk about equilibrium when you can measure the voltage and track electrons moving through wires, which is pretty cool. And we will do, at the end of this chapter, if you look ahead, there are applications to this, to the pH electrodes that we use in class, and I'm even going to draw a parallel between the potentials across a cell wall using electrochemistry. So there are definite areas of interest and reasons why we want to understand this. However, we have to get there. And where we start is, we start by balancing redox reactions. And we're going to use oxidation numbers. To do that, I will tell you that balancing redox reactions is much more complicated, and actually we didn't balance them, we just determined oxidation numbers in Chem 400. Anyway, there's going to be two ways. So there's going to be what's called in acidic media. When you're in an acid solution, you always have H+ and you always have H2O. These are aqueous solutions, as we see. Now there'll be a process for doing this. Step 1, assign oxidation numbers. We're going to do the exact same thing we did in Chem 400. What I did in Chem 400 when I taught you oxidation numbers was I wrote oxidation number and then wrote a line on my paper. And then I forget what I wrote down here. It was something like process or, right? Like, these are not the answers. This will be my work to find the oxidation numbers. All right. It's a little hard to see that minus sign for me, so I made it bigger. There's a 2+ over here. All right. So the rules with oxidation numbers, especially as they apply to what we're doing right now, are they're all the same. The biggest one we need to know is that whenever you see an oxygen, its oxidation number is, well, does anybody remember? -2, thank you. And my process work down here says, if I have 4 oxygens and they're each -2, that adds up or multiplies out to -8. And I made my minus sign nice and big because in ions, the sum of the oxidation numbers has to equal the charge. So it has to equal -1. That means that the oxidation number on manganese has to be +7. Wow, that's a very positive oxidation number. Anyway, let me do it a couple more times, and then I'll be happy to take any questions. So, same procedure as last semester, and for this one, actually, I'm drawing these lines because each element has its own oxidation number, just to keep the elements separate. I'll do that over here as well. Oxygen is -2. Hydrogen is +1. I have, again, 4 oxygens. I have 2 hydrogens. There is no charge on this molecule, so I put a 0 there. The number that goes right here in my process to make everything mathematically work is +6. And this time I have 2 carbons that have to add up to +6. What is the oxidation number of each of my carbons? It is +3. And that's because there are 2 of them. That makes the whole process work. And I put it in blue because that's the tricky part. I'll tell you what's not tricky is the manganese ion. It's got a +2 charge. It has to be +2 because the oxidation numbers have to add up to the charge. And if you remember, we had another rule that says monatomic ions have their oxidation number equal to their charge. Manganese +2, oxidation number +2. Sodium +1, oxidation number +1. Oxygen again, -2, there are 2 of them. There's no charge on carbon dioxide. That carbon is +4. So, and that's all Chem 400 material. I will tell you that what I need if I ask you for your, what will now be your 3rd exam, and or on the comprehensive final, for answers for this kind of problem, it is the oxidation numbers I'm looking for. That is the only thing I need to see. This process baloney down here, if that helps you, great. If not, don't write it. Because I will only be grading what you tell me are the oxidation numbers. On the other hand, see this hydrogen? The oxidation number is +1. So if you tell me the oxidation number is +2, unfortunately that's wrong. It's +1, and there are 2 hydrogens. Anyway, we'll have ample practice on this. Any questions about step 1? Kate?
Something by itself is at 0 or something too.
Good question. So one of the other rules is if something's by itself, and specifically that might be something like oxygen. Does that answer your question?
It's like oxygen gas and like hydrogen gas, iodine gas,
Anything, and what I would say is the charge on this is 0. Because there's only one type of atom, its oxidation number must be 0 for it to add up to 0. I know, that's sort of my fallback rule. Any other questions? That's step 1. That was where we ended in Chem 400. Now it's going to step 2, separate into half reactions. So there's going to be a reduction and an oxidation half reaction. I think in Chem 400 we did have you do this. We had you look for what was oxidized and reduced. Manganese went from +7 to +2. Was that oxidized or reduced? It was reduced. Reduced, my acronym was gain electrons reduction. Grrr. So manganese is reduced. And when you divide it into half reactions, you have to write whatever the entire manganese species is, and on each side. So and I would encourage you to leave some space in this half reaction because we are going to be adding other things. Leaving that space was on purpose. Now, as far as the oxalic acid, +3 to +4, that is getting more positive. When you get more positive, you must have lost electrons. Lose electrons, oxidation. Leo, the lion, says, grrr. Now we don't worry about balancing things yet. This is just, we're breaking them into half reactions, and we want to make sure that the oxidized and reduced species, right? So who cares about the oxygens yet? We're going to balance for mass next. Any questions about this? All right. I'm going deep into my bag of tricks for this one. Uh-oh, I'm out of tricks.
Check out your sleeve.
So I really wanted a red marker, and I'm not finding one. Thank you. That's brilliant. And it works. It's a two-step process. This is a six-step. All right. So now balance for mass. That's going to be in red, I'm happy to say. Thank you for your help. All right, and so balance for mass as far as atoms goes, and you can see the results over there, but I'm still doing it over here. So I have 1 manganese. You always start with the manganeses first. They're balanced. Now I have 4 oxygens. On the reactant side, I need 4 oxygens. Here's where the H plus and the H2Os come in. You add oxygens by adding waters, H2Os. And so I add 4 H2Os to make my oxygens balance. And then I add H pluses. You add H pluses last, because when I add H pluses, it doesn't screw anything else up. Now I have 0 hydrogens and 8 hydrogens. So I add 8 H pluses. That is balanced for mass. Let me do the same thing down here. Always start with the thing that's being oxidized or reduced first. I have 2 carbons here. I only have 1 so far. Added 2 coefficient. Now my carbons are balanced. Then do oxygens. Are my oxygens balanced? Yes, they are. Then I can move on to my hydrogens. I have 2 hydrogens on the left. I add 2 H pluses on the right. Everything's balanced for mass. And we should get to the answers right over here, lo and behold. If I've done everything right. Although, that's a good safety mechanism. Then we go to step number 4, balance for charge. I've actually mentioned this a couple times over the last semester and a half that we've been together, most of us. Now I'd like to really hit home with it. When you balance for charge, I see, so it just means whatever the charge is on one side, it has to be on the other. I'm gonna, this permanganate ion, its charge is so tiny. If I add up the charges on the left-hand side here, I get plus 8 minus 1, that's plus 7. On the right-hand side, I get plus 2. Now, when I balance for charge, I'm going to be balancing by adding electrons. Electrons are negative. Therefore, I'm going to add enough electrons here to make both sides plus 2. And again, sometimes it'll be 0, sometimes it'll be plus 2, sometimes it'll be minus 4. We have no preconceived notions about what it will be. Our only conceived notion, not preconceived, is that it will be the same on both sides. Now we come down here, we have 2 H pluses, we have no charge. Now both sides have 0 charge. So it could be plus 2, could be 0, who knows. However, do make sure that your oxidation half reaction, you have to be losing electrons. That means electrons have to be a product. For oxidation, electrons have to be a product, meaning that's what it means to be lost. For reduction, electrons have to be a reactant. Right, because what does reduction mean? Something is gaining electrons, those are the electrons. Have I used E superscript minus for electrons in here? Have we talked about electrons in here? Yeah. In 400 I know we did. Well, just in case, E superscript minus means electrons for me. And we're going to be talking about electrons a lot. All right. If there are no questions, then let's keep moving on. We've got step number 5, multiply each reaction to cancel electrons. I have 2 on the bottom, I have 5 on the top. Here's where we use our least common multiple skills. And the least common multiple is 10. So the bottom reaction is going to be times 5. The top reaction is going to be times 2, because the electrons always cancel out. The electrons always cancel out of the overall redox reaction. All right, where did I put that in my notes? Oh. And then we're adding them. Have I mentioned how one of my favorite things to do is add reactions? All right. Well, I'm going to let you know now. I have 10 electrons, 5 times 2 electrons on the product side. I have 10 electrons on the reactant side. That's by design. Of course, they cancel. Now I just write what's left. I have, and let's see. I have some H pluses here. I have some H pluses down there. My particular method is just to write everything out and then cancel it. That keeps it simple for me. Here we go. I think I get everything. Well, hopefully I did. We'll see. And I don't care how you get this overall reaction. I'm not done because I have 16 H pluses here and I have 10 H pluses over there. Anything that's on both sides you can cancel out. Get rid of all 10 of them, leave 6 on the reactant side. I don't think anything else cancels out, is that right? So, cancel anything on both sides. Final answer, everything that's left. I'm going to write it one more time. And while you write that down, let me point out to you that you cannot balance redox reactions by inspection. Right? I'm going to come to the back here and admire my work. Wow, 2, 6, 5, 2, 8, 10. That was my phone number in kindergarten for a landline. Anyway, don't try, right? This process only works because you're very explicitly canceling out your electrons, and so do the whole thing. All right, any questions about this? Hannah?
What's the significance of balancing redox reactions? Like, what are we, I mean, I know we're obviously moving forward, but like, I'm just kind of...
Great question. What's the significance? Well, this is what we do stoichiometry with. So if you put this and this in a beaker,
What's happening?
you could figure out how many grams of each you need. I mean, that's at least one example. The bigger example is that we're going to have, we're going to go through balancing them, and then we're going to work with balanced redox reactions. And so we want to know where they come from, and then we're going to use balanced ones, and then we're going to use, and then we're going to start, see those 10 electrons that canceled out? We're going to actually pass them through little wires and light up light bulbs.
So they're
With-
basically like leaving, they're leaving, one's leaving as a product.
One's leaving as a product. Right. Oh, so yeah. So these electrons, in theory, it won't be this exact example, but in theory, we'll take these 10 electrons and this is pretty cool actually. I didn't think about this before because these reactions will be coupled as well. However, these reactions will not be in the same place because we will pass the electrons from one place to another. Interesting. Anyway, we'll think about more about that. What does it mean to be coupled? These are reactions that are coupled but are not in the same place. And that's how we pass the electrons through the wire. Anyway, does that answer your question, at least some?
Yeah, I mean, I'm pretty sure it'll be answered.
Yeah, no, so yeah, that's like, we need these reactions pretty much.
Okay.
We need to do stoichiometry with them, and we need to know things like, when you have the electrons, make sure they cancel out.
And this is just like an acidic.
This is an acidic media.
That's why we see like H plus and H2O in our final.
You got it, H plus and H2O are in our final answer. The other case is in basic media. That's on the next slide, which we have plenty of time to address. In basic media. In basic media, there are actually two ways to do it, and I don't care which way you do it. I think this is the simpler method. In this method, you solve the problem as if you were in acidic media, then neutralize the acid H+. If you look in your book tells you how to do it both ways, and the sort of the other way would take hydroxides and H2Os and use them in the same way that we just use H pluses and H2Os. I think it's more complicated because every time you add an OH, you screw up your oxygens and either way you want to do it. But when I do it this way, it is not true. You cannot pretend you're in acidic media and then put it in, or we are pretending, let's say. Anyway, so final answer for the last problem has 6 H pluses on this side. When I neutralize them, I'm going to add 6 OHs, 6 hydroxides, that is. And whatever you do to the reactant side, it stays balanced as long as you do it to the product side. What do you think 6 hydrogen ions and 6 hydroxides make? They make 6 waters. You know what the Kc for that process is, going from these ions to 6 of these waters? 1 over Kw. That means 1 to the times 10 to the plus 14. Yeah, that happens. And that's actually H plus and OH. Well, we typically call it H3O plus in the acid-base chapters. Still, it's the same thing. And yeah, it's basically strong acid, strong base titration in a nutshell. That's why I use the term neutralize there. Finally. Now I have 6 H2Os. And I have 8 H2Os. I can cancel some of them. We'll do that in my fancy new red pen. Oh, I'm sorry. There's a typo. See this 2 right there? There should be a 2. Sorry, that's a typo. And a 2. I missed that from my notes. That's what the pink means, is typos I found. Typos, there you go. Now, I can move on to red. Leaving two H2Os over there. And then, like always, like I did last time, final answer in basic media. Oh, I threw in an aqueous, didn't I? Anyway. I'll erase it just for you. Question. I didn't do any phases in this. Do you know what the phase typically of a permanganate ion is? I'll give you a hint. It's charged, and everything that's charged is in the same phase in Chem 400-401. It is aqueous, yeah. Oh, let me pretty much, I know, we might have seen one or two that wasn't, and it said not aqueous right after it, too. This will dissolve in water, dissolved in water. We've got water all over the place here. We are producing a gas. This gas will escape. Carbon dioxide is a gas. A little of it will dissolve, and then of course we've got our solvent. Note, the same reactants will often react differently in acidic and basic media. The above process is only a shortcut for finding the right answer once we know already that the media is either acidic or basic. Maybe what I should say there is disclaimer. James and then Marissa.
So what happened to the OH, the 6?
Oh, thank you. Was that your question, Marissa?
Yeah.
Thank you. I apologize. Yes, of course it's still there.
Wait, what other side?
Wait.
I thought it was on the.
Oh. Okay. I saw it up there.
Yeah.
And it makes me feel better to know there was in my notes. I just didn't see it.
So in theory, could we see a problem where we have to figure out if a solution is acidic or basic, and then we have to figure out this stuff resulting from that?
Good question. So the question will either say balance this reaction in acidic media or balance this reaction in basic media.
So you won't have there won't ever be a situation for us where we don't know.
Correct.
Okay.
Yeah. I mean, I guess if I really pushed it, which I probably won't, I can't imagine doing this actually, I could say balance this reaction when the pH is 12. And then you might be expected to know it's basic media. But that's
So if you're asking balance this reaction in the like basic media, would we have to then balance it in an acidic, and then we can work through it and do this shortcut?
yes. So if the question says balance this reaction in basic media, I would suggest balancing it in acidic media and then using this process to get to basic media. Well, the next slide, which involves voltaic or galvanic cells and the series of information based upon it, takes about 20 to 30 minutes of lecture time. So at the risk of turning you loose early, we are done for today. And that's where Professor Ishchuk will pick up on Monday. I will let him know.
So that time up?